My name is Gijsje Koendrink and I work at the Technical University of Delft in the Netherlands. My work revolves around cell and tissue mechanics. So I take a biophysical perspective to understand how cells and tissues function. And the idea here is that mechanical properties are very important for cell and tissue function, because cells and tissues need to be mechanically strong, because throughout the body cells and tissues are exposed to large stresses and strains. But of course at the same time cells and tissues need to be dynamic, so they can actually actively change shape. And we are very curious about the question how it's possible that cells and tissues are able to combine strength with dynamics, because this is something that you don't find in typical man-made materials, but somehow living matter can combine these very contradictory properties. Yeah, the tools that we use range across different skills. So we do experiments, often in close collaboration with people who do theoretical modeling. And cells and tissues are of course really multi-skill systems. They're built of molecules, but molecules make larger assemblies, which then form macroscopic cells and tissues. So we do very macroscopic measurements, where we deform whole cells or rebuild pieces of tissue. But we also go down to the molecular level, so we also use optical tweezers to do measurements at the single molecule level. Yeah, so for us they can do a number of things. So on the one hand we use it to look at mechanical properties. So to measure the mechanical response when you, for instance, pull on something on different scales at the molecular level, and then we want to correlate it to the mechanical response at the cell or tissue level. But we also use optical tweezers to measure interactions. So for instance, cells are held together by a cytoskeleton, and the cytoskeleton is a network of filaments that's held together by crosslinkers. These crosslinkers bind very transiently and they also respond to mechanical load. So with optical tweezers we can actually measure the binding strength in lifetime. Yes, of course you need it to simply visualize what you're doing, but I think a very nice new application is also to look at mechanochemistry. So one thing we've started to do recently is to look at enzymes that are important for turnover of the extracellular matrix. So there's enzymes that break down, for instance, collagen fibers, and there's some evidence that these enzymes are mechanically regulated, and we are investigating that using a LUMIC system. And here we can do dual color imaging so that we can see the filament but also the enzyme, so we can visualize how the enzymes bind and cut a fiber while at the same time controlling, for instance, tension.